Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good morning. It's my pleasure to introduce Pascal Fier. Pascal and I, we actually both got the PhD from India and Olivier Faujas. But he spent most time at SRI, and now he's a professor at EPFL in Switzerland, in Lausanne. So he will talk about deformable object modeling today. So Pascal.
Thank you. So yeah, I've actually retained an interest from our days at INRIA in 3D geometry. So today it's going to be 3D geometry of deformable surfaces. And the game is going to try to get the shape, preferably using a single video camera, of a deforming surface. And the reason we got into this is the America's Cup. So as you know, Switzerland is a big maritime nation. And, but it has nevertheless won the America's Cup twice now. And the idea is we are supposed to help them keep it. And to do that, what we've been asked to do is to model the shape of the spinnakers from video. And actually that's a very good example where doing things from video is good because these things are huge. These things are 100 feet tall. You could maybe scan them using other devices, but it wouldn't be all that convenient. Video is what's needed. And another very important point, which is why I usually show this slide, you want to know what the competitor is doing as well. So you could conceivably have sensors on your own boat, but it's unlikely that you'll have sensors on the competitor's boat. So that's really a case where video is good. So we've been working on algorithms to do this. And the reason, of course, being that what the sailors want to know and the designers want to know is, do their sails behave the way they should? They've simulated them, but they want to know whether what they've simulated is really what happens and how they could improve it.
Are you talking about the frame or is it about the...
I'm sorry?
Are you talking about the frame of this? Because I'm not familiar with the knowledge of the boat.
Right.
So
The spinnaker is the big bell-shaped...
the shape of the sail.
The shape of the sail. So we want to recover the 3D shape of the sail. And right now, in what I'll talk about that a bit later, we gave them a system to do this offline. But now in the current phase of this project, we are working on this boat and another one. We want to go real time. And the idea is, in real time, you would have a readout of the shape of the sails and how you should change the trimming of the boat to improve performance.
And that's legal according to the sailing rules.
That's legal. Actually, it's a self-defeating thing. Is the reason video is allowed is because people assume you couldn't do anything with it. Once we've demonstrated that you actually can do something with it,
right,
it'll be banned.
Right.
But that's okay. The student will have had his PhD since. And actually, we have other projects up our sleeve. And that's another project EPFL is interested in, which is called Solar Impulse. So Solar Impulse is a plane that's powered by four electric engines with a bunch of solar cells on the wings. And the idea is someday, the dream is, someday it will go around the world, so full circle, on solar power, no fuel. And well, in this day and age, actually, I guess that's a good kind of project to have. And turns out that to do this, what you need to have is a plane that's very light, with very big wings, so that you can have lots of solar cells. So if you say big wings, very light, you say very flexible. So the wings will really deform a lot. Actually, the wings of old planes deform. But the planes of this one will deform even more. And it's the same kind of technology. You want to be able, during the flight tests, to understand what's truly happening. And okay, so I've given you two examples which I like because in a university settings they are great projects. I mean, they get the students motivated. It's not hard to get students to work hard on something like this. But this has lots of other applications in more mundane matters. For example, if you think of a crash test, You send a car against a wall, you want to know how it deforms. You will also have deformable surfaces that you want to measure.
But people have been doing this for years.
Yes, they have, but sure, but they put markers. And they get information only where you have the markers. You don't get the fine information about what happens between the markers.
Well, okay, if you talk to the automobile companies, in Ford, or everybody has a big office, a big team working on geometrical modeling. I mean, they take a couple of points to deform the surface, and then they do the crash test.
Sure, but if you do that, you look at the cars, they have targets.
I mean, the real car. You're talking about scanning.
No, I talk about the real crash tests. You go to a car company, and it's really heavy. It can be done, but it's a heavy thing where you have to very carefully put all these markers, and it's like motion capture of people. You can do Vicon where you put markers and you get what people do, but you get only very discrete measures. If you want to get finer measures, then it's useful to have the video in between. And then, there's also all sorts of other applications. I'll get back to that. Things like, for example, if you model how clothing behaves. In the medical case, our insides are full of deformable surfaces. I mean, the list is long of things that this could apply to. And okay, so what I'm going to do is present a bunch of techniques to handle these problems using different assumptions on the nature of the object we're trying to track. And in all cases, I am going to be in a fairly standard framework, which is the framework of the deformable models, where what we have is an objective function we want to minimize with respect to camera pose and some shape parameters. And that optimization function is going to be, as is often the case, a sum of two terms, a data term, usually based on correspondences, between a model image, which is this one, a model image in which we know the shape, and an input image, which is the image that we get in our video, in which the shape is unknown. And we're going to assume we can establish correspondences between the two. Plus, and of course, as we all know, correspondences are noisy. So not all of them will be good. So you need typically to add a second term, which is a regularization term. And whether this works well or not is usually predicated on how good your regularization term is. And what makes this challenging is, of course, if you have only one view, it's highly ambiguous. Because shapes, deformable shapes, there are many, so given one projection, given one projection that could have been produced by several 3D shapes. So the most obvious one is a scale ambiguity, where two shapes, a big shape far away and a small shape close up, give you the same projection. But there are many others, and this one is an interesting one. It's the bas-relief ambiguity, where it says that if you have a convex shape and a concave shape, the projection is not exactly the same, but it's very close. And given the fact that your correspondences are noisy, it's very hard to distinguish one from the other. And there are in fact many more than this. So what we're trying to solve is a highly ambiguous, under-constrained problem, and we are going to need some form of a shape model or deformation model to solve it. And the challenge we've tried to address in this work is, well, how can we design our models, our regularization terms, so that we make as few assumptions as possible on the deformations? And so in this talk, I will distinguish essentially four different cases. Either I have a very textured surface, which means I have lots of correspondences. In which case, I will show that you can actually get away with very, very weak assumptions on the shape, so that you can model things that deform really strongly like cloth. Or you have poorly textured surfaces, in which case you have far fewer correspondences. If you use something like, instead of correspondences, you could use, of course, template matching or any of these techniques, but it would be the same essentially. And then you do need some form of deformation models. And I'll talk about global deformation models, which essentially assume smooth deformations, and I will expand them to more local models that can also handle complicated deformations such as those of cloth. So let's start with the case where we have a well-textured object, surface we want to model, which means we have lots of correspondences. And here we are going to pay homage to Olivier, our common thesis advisor, and go back to projective geometry of the, essentially this is 90s stuff, but it still works, where the problem we are now facing in this case is we have a model image in which we know the shape. We have an image we're now looking at in which we have correspondences. And we are going to assume that we model the surface as a triangulated mesh. So on that triangulated mesh, we have points for which we know correspondences. And these points on the 3D surface can be defined in terms, they belong to a facet, and they can be defined in terms of the barycentric coordinates into the facet, to which they belong. It turns out that if you look at this, every correspondence gives you one linear equation that relates the 3D coordinates of the vertices to the 2D projections. And when you do this, it's essentially equivalent of doing a DLT. Which means if you have a whole bunch of correspondences, you can create the vector y, and the vector y here is the vector you get by, you take the 3D coordinates of all the vertices, you make a great big vector by concatenating them, and this set of linear constraints can be written in matrix form as my equals b, where m and b, m is a matrix, b is a vector, which are given by the correspondences. So once you've written that, you could say, great, it's done, except it's not, even if you have infinitely many correspondences, because if you look at the eigenvalues or the rank of this matrix M, it looks like this. And what's to be noted in this graph is there's a very sharp drop here. There are 2/3 of the eigenvalues are clearly non-zero. And the last third is not exactly zero. In fact, only one, which is due to the scale ambiguity, is exactly zero. But these are very small. And this is actually fairly easy to see. What's happening is the correspondences constrain the vertices of the mesh to be along particular lines of sight, which constrains 2 of the degrees of freedom, but lets the third one poorly constrained, which is exactly what you see here. And that's a way of formalizing these ambiguities I've been talking about. So if you solve it just like that, you give that to MATLAB, you get essentially junk as a result because of these small eigenvalues, a little bit of noise in your correspondences, and you'll get crazy results. So what you need to do to solve this is to increase the rank of the matrix M. And the question then we've tried to answer is, how can you do that without making lots of assumptions on the surface? For example, without assuming that it deforms smoothly, because it doesn't necessarily do that. And it turns out that one good way of doing this is to replace the spatial smoothness that's often used by a temporal smoothness. By saying, well, I don't know exactly how the surface deforms, but I know, or I assume, that the vertices don't jump crazily from one frame to the next. So where I'm going to put are constraints of how much they move from one frame to the next. And I'm going to do my reconstruction not on a single image, but on a sequence, because I'm dealing with video sequences anyway. Which means that if I have capital T images, I have one of these systems for each image. I can express that in matrix form by putting a matrix with a block diagonal matrix here. And here I put all my y vectors and I concatenate them. If I just do that, I haven't gained anything because I haven't linked the frames. But where I can win is by saying, well, I'm going to add a bunch of constraints that say I cannot move more than a certain amount from one frame. Each vertex cannot move more than a certain amount from one frame to the next. Or alternatively and almost equivalently, I'm going to minimize the amount, I'm going to find the solution that minimizes the amount of motion from one frame to the next. And it turns out that these additional constraints allow you to add lines to your big matrix and to increase its rank until eventually it becomes full rank -1, and the -1 is the scale ambiguity, which you can't get rid of.
So you do assume you track all the points. You assume you track these points.
I'm assuming I'm tracking the points in 2D.
Okay.
So I have correspondences in all the frames.
Why do you have a scale ambiguity? I mean, you know, for example, the length of the boom or the length of the wing or things like that, right?
It would go away, but I'm not making this assumption. I'm assuming nothing. So it could shrink.
Uh-huh.
At this point, in this case, I'm not explicitly saying that it does not shrink.
Okay.
But I will do that later, but here I'm trying to even not do that.
The configuration of the mesh in the very first frame, is that also, that's not fixed somehow?
Yes, I'm going. Yeah, in the first frame it is fixed, and then you get it to be full rank. And what's interesting about this is now if you look at the eigenvalues of this big matrix, here's the kind of graph you get. All the eigenvalues are non-zero. It's full rank except one, the last one. And the eigenvalues for the first few, the first 2/3, have roughly the same shape. Which is one way to say that at least these modes you haven't perturbed by adding your constraints. You haven't assumed anything about how it deforms, in other words, or very little. And that's actually pretty nice because it allows you to get the deformation or something like that, which is fairly complex. It creases, and we still get the deformation out of those constraints, which if you are using a standard smoothness constraint, you couldn't do that. So of course, and I'll come back to that, this is extremely textured. And of course, this is not an accident. Yes?
Do we assume that each tracking point is visible in all frames?
Yes, we are not handing occlusions here. In some sense, this is more of a theoretical proof of concept than a working algorithm. Okay, so this works with one little caveat is, as I've said, what we essentially do here is a DLT, a direct linear transform. Or it's the same spirit at least. And as you know, when you do that, you lose in accuracy. Because what you are minimizing is not the true reprojection error, it's something else. So typically when you compute fundamental matrices and the rest using DLT, you do that and then you do a bundle adjustment or you do something to get it more precise if precision is needed. And it turns out that in this you can actually also minimize a true reprojection error if you use the SOCP formalism that Frederic Kahl and Richard Hapley introduced a while ago. It's been known for a while in other disciplines, but it was introduced in our field a couple of years ago, I think. And what is this? So it's called, SOCP stands for second order cone programming. And what it is if you can formulate your problem in those terms, find a vector y such that this kind of equation is satisfied for, there are m such equations, and you have to satisfy them. There are ways of solving that. It is a convex optimization problem, and when you've said convex, you've said it could be easily solved. There are good solvers for that. And it turns out that our reconstruction problem can be formulated in those terms. So let's go back. I have said that every constraint, every correspondence gives us a linear equation of that sort. So we can just rewrite it. It becomes this. This is what we're trying to minimize. And it turns out that minimizing this for each correspondence can be expressed as, well, you take this, you send this to the other side, you multiply by this, and what we want to say is for each correspondence, we want the reprojection error to be smaller than some gamma, and that is an SOCP problem. So they are good solvers for that. And so the way this is done, gamma is the maximum reprojection error you're willing to tolerate. So it's not known a priori. What you do is you solve the problem several times, and you find the smallest one for which there is a solution. And because it's convex optimization, it doesn't cost you that much to do this several times. The one problem with this, and that's people have complained about this, is if you just do it this way, it is not robust to wrong correspondences. Because as soon as you have outliers, it will produce a bad result. However, this can be solved fairly easily because once you have outliers, the ones that give you the worst, that satisfy the constraints the worst, are the outliers. So the way you handle this, you solve your problem with all your correspondences, you look at the ones for which that essentially gives you, that satisfy the constraint least well, you remove them, and you run it again until you find a gamma that is within the threshold that you fixed.
So you start with large gamma?
You start with all your correspondences, you run the algorithm, you look at the ones for which this, instead of being inferior, is exactly equal, or almost exactly equal, you get rid of them, and you rerun it. And again, I'm assuming I'm in a world where I have lots of correspondences. So when you do that, essentially in the end, there are enough left that you get an answer. And you get, so that works, but of course not enough, because we still have these ambiguity problems. So for example, if I just do that, given this image, here's what I get. And that's actually interesting. This projects to that. In projection, it looks perfect. But of course, in terms of shape, it's absurd. Again, it's because we have this ambiguity problem. Turns out that we can introduce constraints that are similar to the ones we've introduced in the first case, that say that between consecutive frames, the orientation of the edges can change, but not infinitely so. We can essentially put thresholds on how much we allow them to move from one frame to the next. And these constraints can be expressed as SOCP inequalities. So they fit in the framework.
So can you go back to one? Yeah. So you mentioned that you got that. It's from one frame or from?
From one frame. So now we are in one single frame. As I said, if you do it on multiple frames, it would go away. But
yeah, go on. Thanks.
Okay, so these constraints, which are of the same nature as the ones before, can be expressed in the SOCP constraint, in the SOCP framework, so that it will actually handle something like this, where here, that's a nice smooth deformation, and this is not. And what's interesting about this is I haven't changed smoothness parameters in the algorithm. The algorithm is the same in both cases. It's just the data told the algorithm to do one thing or the other. And here is a complicated, this is a fairly complicated deformation of cloth. And again, that's the right thing. So what you have here is the 3D reconstruction. And here we just, this is just, we just show the instantaneous curvature as a color image. And here we draw the level lines as though this was a map.
How many points actually do you have? How many factors?
We have about, how many this has? It's about 100 facets, 2 or 3 points per facet, so it's about 300. Okay, so just to summarize, up until now, this works on this, but of course this, again, I have 2 or 3 points per facet, which means I have a very textured surface. Well, the real world, unfortunately, is not like that, or not usually like that. So the next step is to try to deal with poorly textured surfaces. And well, then we the first idea is well, actually, the first idea, which is an old idea, would have been to use physics-based models, in the sense that they were first introduced in the 80s. The problem with those is they are physics-based, but it's usually a much simplified physics, Because if you try to model the full physics, it becomes awfully complicated very, very quickly. So you can use these simplified physics-based models, or since now statistical learning seems to be the answer to everything, so in other words, when you can't model, you statistically learn, you can try to learn the possible deformations, which means you create a database of possible deformations, you learn a low-dimensional model from it, and you do your fitting to your data in terms of the parameters of this low-dimensional model instead of the original high-dimensional one. The problem is, creating the database is not always trivial. So for example, one of the well-known examples in the field are the morphable models, Veteran Blunts a while ago. It's a wonderful model, but getting the data was hard work. And it's not clear that you can do that for everything. So what I'd like to talk about now is how are you going to go about creating models, maybe in a slightly more practical way, if you are not in a position to scan the thousands of deformable things. And the spinnaker, again, is a good example. That thing that's 100 feet tall, it's hard to create. If I had to create a database of all the possible shapes of that thing, depending on the condition of wind, sea, etc., etc., it would not be easy. It's probably doable, but not easy.
What are the implications of the folding texture surface? Is it just having
fewer correspondences?
Maybe silhouette becomes more important?
Yeah, both. Which is the implication here. When I told you the matrix was full rank, so that the ambiguities were gone, implicit was the assumption that I have at least one correspondence per facet. And that, of course, goes. And as you'll see in what I'm going to show, we start using the edges. We start using, so we use whatever texture we have in the middle, but they are going to be large areas that are blank. And in some sense, again, this is a bit, what I'm presenting here is not meant to be an end product, right? I mean, if there's no texture, for example, you could use shading. What I'm talking about today is how far can you go simply with texture information and deformation models. But of course, and maybe I'll mention that a little bit later, shading is important too, so at some point we want to use it as well. Okay, so for something like a spinnaker that, when inflated, deforms relatively smoothly, one way we've found a way that works very well to create a low-dimensional model, which is we take the mesh that defines the object. In this case, I'm showing a rectangular mesh, but it could be a mesh of any shape. And it turns out that if you assume that the mesh is inextensible, so this time I'm explicitly making the assumption, a mesh like this one has far fewer degrees of freedom than the 3n it would have if you did not assume that the edges are of constant length. This is because once, for example, for a vertex like this one, once you know where this vertex is, this vertex, and this vertex is, this one has to be at the intersection of three spheres whose radius are given by the lengths of the edges. So you don't have to specify the position of all the vertices to completely specify the shape of the mesh. In fact, it turns out that you can parameterize a mesh like this one by specifying a relatively small number of joint angles, which are the angles between a subset of the facets. And you can show easily that, in fact, this number is almost directly proportional to the number of edges at the border, which is far smaller than the total number of vertices in general. Which means, because you have this parameterization, you can sample it. So you can artificially create a database of feasible shapes and then run the dimensionality reduction technique to create your low-dimensional model. And in fact, in this case, the one that works best is the simplest, which is PCA. You just run you take this, you sample possible shapes, you run PCA, and you get deformation modes. so that you can express your shape as a rest shape, which actually does not have to be flat. In the case of the spinnaker, it isn't. It's a bell-shaped thing, plus a weighted sum of deformation modes. And your optimization variables become the weights that you assign to the deformation modes. So for example, in the case of relatively smooth deformations, and this actually runs in real time, you can wave the piece of paper in front of the camera and it will reconstruct a 3D shape. Or you can stretch the thing, and again it will get the deformation. And of course this works because underneath here is a logo, which means there is some texture. And that's actually in the case of the system we delivered to the sailboat team, the sailing team, is based on that idea. So we have the spinnaker, we have a model of the spinnaker in its rest shape, which is the model that was used by the sail maker to actually cut the panels of which the thing is made. Which means we could compute the deformation modes and fit it to our videos. So the yellow dots here that you see are reprojection of the 3D models onto the spinnaker. And in this case, of course, we have, so that's an interesting case. We have some texture here, and of course we use the Euclidean contours as well to get this. And one, actually, something I would think as an interesting extension, which we have not done yet, but is to look at the shading. To us as humans, I mean the shading, I think disambiguates a lot of things. The problem is if you're going to do shading in this context, you are not going to assume a point light source. And it's a good example. Yes, the sun is in the sky, but the water reflects the light, so it's actually lit from everywhere. And just to make things a little bit more interesting, the spinnaker is translucent somewhat. So it's a very interesting shading problem, but it's not an easy one.
So in this example you deal with occlusion then? Because the last one is
yeah, it's dealing with self-occlusion, which is easy in this case because we have a 3D model.
It looks like there are some errors down near the bottom edge. Is that because the sail actually stretches?
Here, yeah. Well, it's because we are, okay, the main source of information is here, right? So there's a little bit of constraint here. It just has to be that the edge here is not pretty good, probably. If you look at the contrast here, it's very, very weak. So I would suspect that's what's happening. What we did actually, maybe we did validate this in terms of what they want, the measure they want. They don't care about pretty pictures, of course. What they want are measures of the curvature at various levels of the sail. And so we ran some simulation when we create synthetic images, and with one camera we get within, I think, 3 or 4% of the real value, of the true value. So we get that with one camera. This technique, actually, you can use more cameras if you want. So you get, of course, better results in a case like that. If you have one camera that looks from one side and the other camera that looks from the other side. And then we get it down to 1 or 2% with more than one camera.
So you did try multiple cameras?
I'm sorry?
You did try multiple cameras?
We don't need to, but we improve.
Okay.
The more, I mean, not the more. I mean, I think if I remember the curve correctly, 2 cameras improve noticeably, 3 cameras, 2, and after that, okay, it doesn't help that much to add additional ones. But they don't have to be in a closed baseline. Actually, it doesn't help if they're in a closed baseline arrangement. It's much better if they're in a wide baseline arrangement so they see different sides of the sail.
So you don't really do stereo?
No, we don't.
Okay. By the way, so the model you use, you said it's directly from the guys who designed it.
Yes, it's a...
That means for each different cell, you have to use a different geometry.
I'm coming to that. That's the next technique. Yeah, you're right. This is the weakness of that technique.
That's fine.
It works. I mean, many cases these are cases where you do. If you think of the wing of an aircraft, you have the model. but I'll get to that in a moment. Okay, and one more example of the same. They have different sales, so we do have different models loaded in the system. And one actually thing we've recently realized about this is what you've seen here is essentially a tracking algorithm, because we get the shape in one image, and then we get the shape in the next image by optimizing and starting from the previous position. But it turns out that there is something very nice about this linear formulation is actually you can find your solution in closed form, which means you can have automated initialization of the algorithm if you assume the mesh is inextensible. So why is that? You remember that I've said that these correspondences give you an equation of the form M, which is given by the correspondence y equals b. If you express everything in the referential of the camera, then the b vanishes, and it's a simple my equals 0. Y are your unknown. And M is this matrix which is not very well conditioned, which has a lot of very small eigenvalues. So one way to say that is to say that Y is a weighted sum of the eigenvectors that correspond to the very small eigenvalues. When you've said that, your unknown are these betas, the weights you gave to those eigenvectors. If you now add the constraint that the mesh is inextensible, it means that the distances between vertices are preserved, and that gives you a bunch of quadratic constraints of that form. So, and you have actually more constraints of that sort than you have betas. So in theory you can solve this in closed form. So a system of quadratic equation can be solved in theory, except if you just do it, if y is the vector, all the vertices of your mesh, it's a large number of equations, and it explodes. The solver dies a miserable death. So if you don't want the solver to die a miserable death, what you can use is the fact that you can express all this in terms of this linear combination of modes. And this is linear as well. So you have the shape depends linearly on the modes. The equation are linear in terms of the shape, so it's still all linear. And you can express what you are trying to solve. So you have your shape y, which was rest shape plus this matrix x, S, which represent the modes, times A, which are your unknown. These are the parameters, the weighted parameters you give to your mode, has to satisfy this equation, which is equivalent to the previous one. And we've added one thing here, is this matrix W, which is a diagonal matrix, which says that some modes, you penalize more some modes than the others. When you do modal decomposition, that's what you normally do. Again, it means that your vector of weight A has to be in the kernel of that matrix, can therefore be expressed as a weighted sum of eigenvectors of this matrix, of this bigger matrix than the previous one. But you now have far fewer variables, because your variables are not the xyz's for every vertex, they are the weights you give to the modes. And it's still a set of quadratic equation in terms of those modes, and that now you can solve in closed form, which means you can have, in one image, you have a bunch of correspondences. You have your model image in which you knew the shape. In closed form, you can compute the shape in a new image. And it's actually very useful in practice, because if you do tracking, you lose sometimes. Your algorithm will always fail at some point. With this algorithm, you can get the shape really from a single image without prior initialization, which is absolutely essential if this is ever going to be a real-time working system. And so here are examples of how this works. So what's interesting about this is what you see on the right is done on each frame independently. We on purpose, to demonstrate that it works, we have not enforced temporal consistency. So it shows you it's reasonably stable. So of course, after that, if you want precision, you would bundle adjust. But even without doing it, it's already reasonable. Okay, so last topic, which is, and that's the point you made, the technique I've just shown works if you have a global model of the surface you want to model. But that's not always available. So how are you going to go about modeling, creating a model for a shape that is made of, say, a known material, but arbitrary shape? Well, one way to do this is to observe that, assuming that the surface you are looking at is homogeneous, has homogeneous properties, you can actually learn local models, by which I mean deformations of little patches of that surface. And the way you would do that, or we do that, is you take a piece of material, we put Viken markers on it at regular intervals, we wave it in front of the Viken system, and we get tracks, 3D tracks for these patches. And every patch can be considered as an example of what that surface can do. So each of them is goes in our training database, and because we take all the patches from the surface, even with relatively short sequences, we get a lot of training examples. So we put that in our database, we learn a local deformation model for how a patch can deform, and then to form the global model, we simply use a product of expert framework. We take the likelihood to be the log likelihood to be the sum of the log likelihoods for the individual patches. The particular model we use to model local deformation, we use Gaussian process latent variable models, mainly because we've used them a lot in the past, so we've kept on using them. I believe actually for those local models you could use PCA just as well. It would probably give about the same result. But the important part is we get a prior for local deformations. And we can assemble them into a global prior for the whole thing.
So how big a range is your local?
5 by 5. So on something like this, the patches are 5 by 5. And they're overlapping. So we take all the overlapping patches. And what we get is something like this, where now we have something in which we have really little texture. In this case, we have, if you look at this thing, it has some texture here. We use the edges, but there are large areas in which we have absolutely no information. And nevertheless, because it has a decent prior, it can get this fairly complicated deformation. And this speaks to your question. Your earlier question is, now let's take something made of the same material, but different shape. And different shape because especially we've cut a hole in there. So we also changed the topology of the object. Doesn't matter, we can still compute our product of expert on this mesh. It's the same local experts, but the topology is different, so we get a different global thing, and it works in this case as well. So that gets around having to learn a new model for every new object. We learn a model for a specific material.
If you change the deformation, the thing that's forcing the deformation, for example, if you're actually just shaking or if you're actually blowing air, the deformation is going to be different in nature. So it's not a question of the material, it's the material and the deforming action, right?
That's a good question. Is it? Because essentially you want to know how flexible the material is locally. And then it's an experiment we have not done and we should do. But I think the global property is given by once they are assembled. I'm not sure. I mean, do you really think it would behave differently? Because the physics, how much it can stretch, basically, is a property of the material, not that much a property of the. Okay, if you pull hard in your.
If it was rubber,
right.
Just doing what it's doing,
you wouldn't learn that. Okay.
You wouldn't learn it can stretch, right? You just shape it.
Right. Okay, so.
There is interconnection between the patches. if you do dynamic simulation,
Mhm.
there is 90% of dependence. But
There is dependence here too, right? Because the patches are overlapping.
Yeah, but that's kind of it's not strong. It's actually.
But we don't want them, we don't want them to be too strong, right? We have this back in our mind is what are the minimum constraints we can have and still have the thing to work.
It's a good one, but I'm just saying that it may not be physically correct one. I guess that's what you're saying.
No, but I think that, okay, you have a point. As soon as you have statistical learning in there, you learn what you have trained it for. So you kind of have to know if you are in a case where really you are going to have people stretching the thing, you better have this kind of motion in your training data. Okay, so just to tell you that this is not only for sailboat racing and other amusing things. These techniques actually have practical applications. And this is an example, for example, for wings again, but in a much more industrial context, where these people were interested in knowing what the effect of putting winglets. If you put winglets on a wing, and depending on the size of the winglet and the angle of the winglet with respect to the wing is going to deform in various ways, depending on flight conditions, and you want to measure that. And as you point out, you can, of course, do it by putting targets, which actually they did. But if you could do that without the targets, it would help. And one thing that's also very interesting in this is these kinds of techniques give you a way of closing the loop, which is the engineers, of course, have finite element methods to simulate all this. But you want to check that what you simulate is what truly happens. And so that's actually some of the things we are working on for this solar impulse. So this plane is actually not built yet. It's being built as we speak. However, what we have in the lab, we have a 2-meter wingspan scaled down model. And the idea here is we want to know whether we could get something in a real world. And the scenario we have in mind is these people don't want us to touch their airplane in any way, shape, or form. Right? So we have to be able to do this. So the simplest thing would be to put cameras on the plane itself. But they don't hear about that because cameras, we have to touch the airplane, they need electricity, and they're already short on electricity. We have to be away. So the idea is this is a slow flying plane, so we can imagine, at least from the initial flight tests, to have a car in front, and it flies slowly. So that looks at it from below, which is kind of this view. So we've simulated that in the lab. That's about what you would see. And okay, so this is not incredibly, the deformations here, they are grad student induced deformations, but the green thing is the outline of the wing is what the algorithm computes by following the outline of the wings. And the curves on the right side are measures, I think it's the height of the wingtip with respect to some reference. And we've actually tried to validate this, and our simulation give us that on the real plane, when you scale it up to what the real dimensions would be, you would, in that configuration, you could measure, it's 60 meter long, it's big, and you could get 3 centimeter in height at the wingtip, and probably better than 0.5 degrees in twist angle, which is this, which is what the engineers need during their flight tests. And if you want more than that, you can, because this is done with a single camera, but we could do better with more than one. You could use additional visual clues. So for example, we are not using the contours here. It's purely based on correspondences. So the contours would help, and we could incorporate true deformation models, which we don't have really. But in this case, it's a physical thing. We would have the plans, the CAD/CAM model exists. And we could incorporate constraints if we wanted to go further than that. So I think it's actually a very viable technology for a very real problem.
So assuming if you put in the real application, when the airplane is flying in the air, So what?
You have a chase plane then. But
What chase plane?
they will have a chase helicopter.
Oh, okay.
So the first, okay, so the way this is going to happen is there is a long military runway not far from where we are. So the first flight tests will be on this very long runway. So it's just little hops. And if little hops, the car, the camera on the car will work. If that is successful, then of course they will start flying for real. And then the plane will be followed by probably a chase helicopter.
And the camera itself will move around.
Sorry?
I wonder if that will affect anything.
I hope it doesn't really matter because we don't care that much about the global motion. We discount it. What we want is other deformations. And another, okay, now for a completely different kind of application, which is, as Zheng Yu mentioned, I worked for a long time at SRI in Menlo Park, and these people are interested in work with unnamed three letters agency. And I talked about this to the head of the AI center. He says, "It's cool. We have an important problem. Our military would like to be able to have automated readings of banners. You know, in some parts of the world where people are chanting nasty slogans. And to do OCR on a banner, you want to unfurl it first. So could you use these techniques to compute the deformation, straighten out the banner, and then have OCR run on that?"
Actually, another probably easier, maybe cooler application. I just put stuff there.
Of course, to do augmented reality.
Put Obama and say, Pascal.
Right. Right. We could. But actually, do I have time? Because yeah, we have time. So I can show you. I'll show you it after. We've done it, so I'll show you afterwards if you're interested. We didn't put Pascal, but we did other things. But okay, the point is, of course, this. There are 2 points to this. I'm really glad to be in a school where we can work on projects that the plane or the sailboat rather than for three letters agencies. But however, I think these kinds of techniques there's a wide range of applications besides those I've thought about. And actually, if you have good ideas, of course, since I'm sure Microsoft does products, I'm really, of course, interested. And also, I hope I've shown that what this is potentially a generic paradigm for modeling 3D deformable surfaces from one or more cameras. And the way this could go is you need models in general to model deformations, and you can obtain them using texture versions of the surfaces you want to represent or capture. You can learn the models and then apply these models to surfaces that are far less textured. And that's a fairly easy method to deploy. It's something you can actually do. So the idea is you would have a piece of material, you would wave it once in front of your webcam, make sure it's textured enough, learn the model, store it, and so that next time you see this kind of material, it'll work. And actually, you could probably do a hybrid version of this, which is many kinds of material are partially textured, or surfaces are partially textured and partially not. So you could imagine a smarter algorithm that would track the parts of the surface that are textured, learn the model from that, and then track the rest. In other words, I think there's quite a lot of fun stuff to do on this for the future. Thank you.
Thank you.
So for the density texture of the material, that method based on factorization. So can you comment your method versus the existing factorization-based method?
Well, to the best of my knowledge, the factorization methods work for rigid stuff. There are some
based on, say, try to factor out the camera and the structure and also deformation.
Okay, so these, I think the one that comes to mind is something by Torresani and a few others. In some sense, it's related because they use PCA. So they learn modes. So in that sense, it is related. But the PCA was essentially a small part of what I've shown. And what I've tried to explain is how you go beyond that.
So actually, how many PCA components do you use?
40. Typically for the sale, 40.
For sale, the sale.
40.
40 of them. It's not that many.
Not many, no. Which is why we can get the real-time behavior.
Maybe because they don't deform too much.
No, the sail actually, once it's inflated, doesn't deform that much.
Yeah.
Where it becomes really hairy is when a poorly trained sail will start flapping in funny ways.
If you let it free, I mean, if you let it wind...
Yeah, if it flaps in the wind, it becomes more difficult, but for this particular application, it's not important because they don't care about what happens then. Then it's just badly trimmed. They care what happens when it's correctly trimmed.
So for airplane application, I mean the deformation is really small. I mean airplane is pretty rigid, right? I assume.
Actually, it's not as rigid as you would think. It's on an Airbus, the wingtips I think flap by 1 meter or 2.
A meter?
Oh yeah.
Oh,
Which actually means it's a good thing because it acts as a no as a shock absorber.
Yeah.
If they were truly rigid, the ride would be far bumpier.
Right.
So have you compared the local model with the global model? Have you applied the local model to the sail?
Yes. It works. To the sail, no, but to the smooth deformation, it works almost as well.
Which one? Which smooth deformation?
We have, if you look at, we had essentially a piece of cardboard.
Okay.
And on cardboard it works fine. So it has, it's still slightly less constrained. I think where you lose is it's actually a bit heavier in terms of the computation. Mm-hmm. You have more variables. So we haven't managed to make that real time yet.
Yeah, just one question regarding the sailboat. You mentioned there was no texture at all in the middle, in the center. You mentioned the shading. That seems interesting. I wonder if people have done that by using this to model you got. You have a linear model for your components, and then suppose you have no corners at all. Right. So then you just use your linear model and add this shading stuff there, shapeable shading. I wanted that.
Okay. With some luck, that will be our submission next year.
Okay.
No, it's a natural idea.
Yeah, it seems very interesting.
Because you want to formulate. Okay, so the difficulty in that we haven't. I mean, I'm not sure it will be our submission next year because of that. Is that if you assume a simple point light source model, then the constraints are linear, as the shading can be linearized and it fits in this paradigm. The problem is, well, point light source is it's too strong an assumption to be realistic. So the difficulty is...
But people have extended like phase modeling, right? In the phase, I mean, you have the local model, which is similar to your linear model. And then on phase, people handle the lighting by using the spherical modules to handle the...
Right, okay, so that yeah.
You can do the same thing there.
Yeah, that is a possibility as well.
Yeah, so then you don't have to point that.
Yeah.
Can you use the shading as a cue for the stress around an edge?
The stress on?
Like, the shading gives you the rough shape of the edge, right? You don't care about the actual... if you model the connection between the two triangles,
right,
the shading can give you that information.
Yes.
Not necessarily the face normal, which what shape from shading does, but the stress.
Right. I agree. That's another thing, I think, an interesting lead as well, which is, okay, so we have this ambiguity in general. If, say, we have a simple mesh with two facets. This and that doesn't look that different in projection. But if you know something about the shading, you should be able to tell one from the other. And I think that's also an interesting thing. That's worth looking at.
Okay, thank you again.
Pleasure.